All right, let's see. Here we go. Video number 3 of thermodynamics. So I'm just going to focus on 2 learning goals on this video. We're going to talk about knowing the difference between molar heat capacity and specific heat capacity, as well as performing calculations related to the quantity of material and how much heat it releases, absorbs. Okay. So basically we're talking about heat capacity in this new video. And we're going to talk about the experimental method of calorimetry. Okay, so I want you to be familiar with that as well. Okay, so here we go. Heating curves, molar heat capacity, and specific heat capacity. Okay, so let's go back to our example of boiling and melting water. Okay. It's my favorite example. Water is my favorite molecule. And what I want to point out are some interesting things you would see if you were to start. So here we go at minus 18. Start with an ice cube. Okay? And we started steadily applying heat over some period of time. So on this x-axis here, add heat steadily over time. So you can view this like as we're progressing this way, our material is getting hotter and hotter and hotter. Okay? And then here is the temperature of our material. So you notice that it hits this plateau at 0 degrees and will remain at that plateau for a period of time. So what's happening at this plateau? Well, the ice is melting, and that takes some time. And during that time, the ice is not going to change temperature. It can't, because you can't have a piece of ice at a hotter temperature than 0 degrees. You can't do it, okay? So melting is going on right there, and specifically the heat that's being pumped into that is the delta H of fusion. So heat is still being added, but there's no change in temperature. And that is unique to a phase transition, okay? When we are adding heat, but there's no change in temperature, then all of that heat that we are adding is getting pumped into the delta H of fusion. And so really what's going on, all of that heat is getting pumped into those chemical bonds to separate the waters from each other. Okay? So they're in this nice, lovely crystal structure that we'll talk about in Chem 110. And the bonds I'm referring to are not the oxygen-hydrogen intermolecular bonds, but the intramolecular bonds. So what's keeping, one water molecule next to another water molecule in this ice cube? All that heat is getting pumped into separating them. Okay? So it takes some time. But then now finally the ice cube is melted, and now it's become liquid. So let's see, can I write sideways? So this is now the liquid, okay? And you notice that it shoots up in temperature pretty rapidly, and now hits another plateau at 100 degrees. And so what's happening there? Well, that's called, we'll just say boiling, right? We could say vaporization, but we know that it's boiling. And so all of the heat that's now being added is getting pumped into the delta H of vaporization. And so you also notice that we can't have water above 100 degrees. You can't do it. You cannot have liquid water that's above 100 degrees Celsius. Okay? But finally now at this point, all the liquid is gone. Okay? And now we've got the gas or the vapor, right? And we can heat steam or gas up to an incredible temperature. In fact, when you hear about people having steam burns, it can be quite serious because you can get gases, not only water gas, right, steam, but you can get other gases to a very hot temperature. But you can never get a liquid hotter than its boiling point, and you can never get a solid hotter than its melting point. And this lag time that's going on as we're adding heat is going into the molecules to rearrange them to change their phase. So now what we're going to focus on is a set of equations that's going to allow us to predict what's going on in these various regions of the curve. Okay? And so I'll highlight that by saying on this line of the curve, it's the delta H of vaporization. Okay? So on this line of the curve, I highlighted it's the delta H of fusion. And on this curve, what's happening is the heat capacity, CP or CS, depending on what units we use. And I'll talk about that next, okay? So we have two types of flavors of heat capacity. There's the molar heat capacity, and there's the specific heat. So the molar heat capacity, CP, the P denotes constant pressure. So again, this is our useful laboratory bench quantity, right, where we're just sitting on the lab bench at constant pressure. So that's the quantity of energy required to raise the temperature of 1 mole of substance by 1 degrees Celsius. Okay? So CP has units of joule per mole per degree C. So that's the unit, joule per mole per degree C. So for example, if I have 1 mole of quantity, okay, and I raise its temperature by 1 degrees Celsius, however much joules that takes, that gives me the heat capacity, right? Okay. So, for example, water is 4.18 joules per mole per degree C. Or no, it's not 4.18. Excuse me. I have it right here in front of me. It's 75. So to take 1 mole of water and raise it by 1 degrees Celsius, it takes 75 some odd joules. Okay, so that's what this heat capacity means. So now this formula that we use, okay, so we note that Q is heat. So how much heat does it take? So basically what we're now interested in, right, is this curve. How much heat does it take to increase the temperature of a material? So that formula goes, the heat equals N, the number of moles, times the CP, the heat capacity, times the delta T, which we recognize as T final minus T initial. So if we think about the units of this equation, that's what's going on right here, right? However much temperature rise and however many number of moles times heat capacity gives us the amount of heat we need to make that happen, okay? So now what about specific heat? Well, this is the quantity of energy needed to raise the temperature of 1 gram of substance by 1 degree C. So specific heat, CS, has units of joules per gram per degree C. And the equation is very similar, however, so it's still heat. However, instead of moles, it's now mass in grams. And of course, this is still T final minus T initial. And so as far as which one's most useful in the laboratory, definitely CS, because we don't have a mole-o-meter, right? We have a balance. We have a mass balance, something that gives us the grams of material, not the moles of material. So we use CS far more in the laboratory, but we should note that CP and CS can be interconverted to each other quite easily. I also want to point out, because the unit of, so if you do 1 degrees Celsius, if that equals delta T, let's just say for example, then that's going to be the same as 1 Kelvin. So the value of 1 degree Celsius is the same as 1 degree Kelvin in terms of delta, right? In terms of the change. So these units can also be given as joule per gram per Kelvin or joule per mole per Kelvin. So it works the same. So you could actually keep temperature in Celsius or Kelvin for this particular equation. And the reason for that is because you're dealing with the delta. You're dealing with the change in temperature. And so that's why it works out that way. Okay? So here's some examples. Okay? So here are some examples of CP, joule per mole per degree C. And I want to point out this quantity of water, 75.3. Okay? So CP for water is 75.3 joule per gram per degree C, or the same thing, oh, not gram, mole. Joule per mole per degree C, which is the same as joule per mole per Kelvin. It's the same thing, okay? So example here, convert liquid water's molar heat capacity into its specific heat capacity. So just like everything we've done in this class, we can use the process of dimensional analysis to do it. So 75.3 joule per mole per degree C is CP for water. How do I get CS for water? Well, I just want to convert moles to grams. And for water, 1 mole of H2O is 18.01 grams. Okay, so when I do that, 75.3 divided by 18.01 equals 4.181 joule per gram per degree C would be the CS for water. Okay? But what I want to point out now, if we want to compare heat capacities from one substance to another, we don't want to compare CS, we want to compare CP, right? Because quantities have very different masses, okay? So when we want to compare like mole to mole, it really makes sense to compare, or substance to substance, it really makes sense to compare the CP, okay? And so what I want to point out here, we have some materials that have rather large heat capacities, like liquid water. So I'm going to put checks next to all these ones that are really large, or even ethanol. And then there's a lot of other materials here that have very small heat capacities. And one thing I'll point out here would be iron. So this raises a question. So let's see here. Low CP. So what does that mean for the properties of these things? Okay. Well, let's think about what this thing means again. Okay, so for water, it takes 75.3 joules to heat 1 mole of water by 1 degree Celsius. But for iron, it takes 1/3 of that energy, right? For the same rise in temperature, for the same amount, 1 mole, it takes 3 times less energy. So what does that mean? Well, low heat capacities means it doesn't take a lot of energy to heat it up. So that means that they are very good thermal conductors. Okay? Which makes sense when you think about it. Aluminum, copper, iron, they are great at conducting heat. Okay? Which is why we use iron to make a pan, right? Because if we're cooking something, think about that. Like here's my really crappy cartoon drawing of a cast iron pan, okay? Right? And then here's like a flame cooking over the cast iron pan. Because it has such a low heat capacity, we're going to be able to heat that pan up really fast. And it's not so much speed, I should say, it's really efficiency. So we're going to be able to heat this pan up with a much smaller quantity of energy. Okay? So conversely, the water, because it has 3 times the amount of heat capacity, it's going to take significantly more energy to boil that water or to heat it up. Okay? So this is very, it should be similar to like your common everyday experiences in the kitchen, right? Your metal pans get hot really fast, but it takes forever for that water to boil. And that's because of these heat capacities, which is pretty cool. Okay, so now let's do a sample problem. This one is going to be a little bit more difficult. I'm going to walk you through what we're doing. Okay, calculate the amount of energy needed to convert 252 grams of solid ice at 0 degrees to hot water at 80 degrees. Okay, so what we're doing, if we go back to that heating curve that I showed you, right, where it was temperature, so big T versus time, little t. You know, we're starting at ice, right, at 0 degrees, okay? And we're going to have to, like, let it phase transition for a little bit, okay? So that means the temperature is not going to change. And then we're going to heat it up to liquid water at 80 degrees C. And so schematically, what's going on here, during this leg of the calculation, we're going to have the delta H of fusion, all right? And during this leg of the calculation, we're going to be using the heat capacity. So it's going to be a 2-part calculation, part 1 and part 2. Part 1 is just how much heat do we need to make it melt, and then part 2, how much heat do we need to make it rise in temperature. Okay, so part 1, to melt ice. What we need to do, and I'm going to write that as Q1. Okay, so I don't have a formula for this because it's our stoichiometry, but I'll write a formula. It's going to be N times the delta H of fusion. Okay, and so what that means is I need to convert this 242 grams into moles. Okay, so let's see here. So that means my N is going to be 252 grams of H2O, and I know there's 18.01 grams of H2O in 1 mole. Okay, and so let's see here. So I get 252 divided by 18.01. And with 3 significant digits, I'm going to call it 14.0 moles. Okay, great. So now my Q1 is going to be 14.0 moles times my delta H of fusion. The molar enthalpy of fusion of ice is 6.01 kilojoule per mole. Okay, great. And let's see, I'm going to make that into joules as well. So 6.01. And the reason I'm going to make it joules is because I have my molar heat capacity in joules. So I could do either way. I could make this one kilojoules and keep this one in kilojoules because I want to compare apples to apples. Okay. Oh, and so actually I wrote CS on this little diagram, but because we just converted to moles, we're going to use CP. Okay. So I know 1 kilojoule is 1,000 joules. So that means, 1, 2, 3. So that quantity is 6010 joules per mole. Okay, and the mole cancel. And so now I'm going to leave this number in the calculator and then just say times 6010. And that equals 84.1, it looks like. Yes. 1, 2, 3. So we'll keep it in joules again. 1, 2, 3, 4. Sorry. 8.41 times 10 to the 4th joules. So that's how much energy it takes just to melt the ice. We haven't even raised its temperature yet. We're just melting the ice. Okay? So now we've got water, and we've got water at 0 degrees. So now to raise the temperature, we're going to use now the N times Cp times delta T. Okay? And so this is the equation that gives us this change in temperature, right? So we note that we have 14.0 moles for N. We note that the heat capacity, Cp, is, there it is, 75.3 joule per mole per degree C. And now what about the delta T? Okay, so it's solid ice at 0 degrees initially, and it's going to end up at 80 degrees for the final temperature. So I can now say 80.0 degrees minus 0.0 degrees C. I could have just put 80 in there, but I did it just to be complete for this problem so you can see how it's going to work. Okay, and so now that's going to be 14.0 times 75.3 times 80 minus 0, which is 80. Okay. So now for this one, I get 8.4, 8.43 times 10 to the 4th joules. So this is amazing. Look, both of those numbers came out very similar. And so let's just think about what that means for a second, okay? It takes just as much energy to melt the ice as it does to then heat it up as water by 80 degrees. So now that means my total heat is gonna be this Q1 plus Q2, okay? So let's say that number plus 84100 equals, and I get that to be Q1 plus Q2, 1, 2, 3, 4, 5, 1.68 times 10 to the 5th joules. And I'm going to convert that to kilojoules just because that's such a big number. So in 1,000 joules, there's 1 kilojoule. So divided by 1,000, that's 168 kilojoules of total energy, right? So if I say divided by 1,000, so 168.4, 168 with 3 significant digits, okay? So again, when we're calculating these change in temperatures, when we're doing these calorimetry equations, keep in mind, right, that when we encounter a phase transition, okay, it's got to be the number of moles times the delta H. But then when we're on this rise, when the temperature is actually changing, that's where we use one of the two heat capacity equations, depending on if we have moles or if we have mass. Okay, so keep track of those. And then let's see, what did I say I was going to do? Oh, we're going to keep going here. Let me see, how much stuff do we have? Okay. So let's see here. I think I'm going to stop because that feels like a pretty good amount of time for this video. And I'll record one more for this just so we can not get too overwhelmed. Okay, folks? So I'll see you in the next video.